In this example, I want to show you how we can use nodal analysis to figure out what V naught in here is. Okay, so we need to identify essential nodes and then select one of them as a reference. So in here, we already have the essential nodes. So this one here, actually, these two are the same essential node. So these are just one essential node. This is an essential node. This is an essential node. This is an essential node. So I technically have 1, 2, 3, and 4 essential nodes. So the number of essential nodes, I'm going to write it in here, is 4. That means I need pretty much 4 minus 1 equations, at least 4 minus 1 equations, okay? So I need to identify them. So, but what I do know is the following. You see this source in here? So this source happened to be connecting this essential node to this essential node. So I have an option in here. If I have the reference in here, that means I'm going to have to treat this as a supernode on right and one equation for that. Or I can just simply choose this to be my reference node, and then the number of equations that I need to write is also 2 instead of 3, okay, because one of the essential nodes I already know the voltage across it. Okay, so I'll go ahead and just assume this is my reference node. So it's a good choice for a few reasons now, because it connects this element, and this element, and this element. And I already will give me readily with this voltage in here. So I don't have to write an equation for this essential node, because I know if this is my reference, this will be 50 volts above that reference. Okay, so that leaves me with a couple of other nodes in here, and I'm going to call them either A, B, or 1, 2. Let's call them V1, and let's call this to be my V2. All right, so now what I need to do is I need to write two KCL equations to figure out what these node voltages are. And once I know, I will figure out what the V naught is. Frankly speaking, the V naught is simply V2 minus 50 volts. So all I have to do is just figure out what V2 value is. And of course, I can figure out any other thing in the circuit that I want. All right, so let's write the equations in here. So I will start with node 1. So I'll say KCL at node 1. So the KCL at node 1 is simply V1 minus 50 divided by 80. Okay, this is the current going from the V1 node to this essential node. Okay, plus I know that this should be V1 divided by 50, plus, let me just see, so it's V1 minus V2 divided by 40, okay, which is V1 minus V2 divided by 40. So this is my first equation, and I can clean it up a little bit, and that will be this equation. I went ahead and I did this a little bit of quickly on my own. All right, so let me just highlight, this is the first equation that combines V1 and V2. Okay, so 4.6 V1 minus 2 V2 equals 50. All right, now we can go ahead and write KCL of the second node in here. So KCL at node 2, and that will be simply V2 minus V1 divided by 40. That's this current going here. And the current in here, we technically know it, just we need to pay attention to the unit. This is a milliamp, and everything we have is an ohm. So this here is volt divided by ohm, that's an amp. So we need to convert that, and that will be negative 0.75 amps versus the 750 milliamps. And of course, we have the current going in here, and that current is simply plus V2 divided by 200. And then we have the current of the last one in here, which going in here. So it's V2 minus the 50 volts that we have divided by 800, okay, which is plus V2 minus 50 divided by 800, and that equals 0. And we clean up this equation a little bit, and that equation will be this here, which is simply negative 4V1 plus 5V2 equals 130. Okay, and so that's the second equation. So all we have to do is just go ahead and solve these two equations to figure out what V1 and V2 is. And that will be, V1 will be 34 volts, and V2 will be 53.2 volts. All right, so we know the two voltages. We can use them to figure out what V naught is. So let me copy that image down in here. So here's the image of the circuit. What we're being asked to do is to find the V naught in here. So let me just do that. So that's what we're being asked to do. And simply V naught is just V2 minus 50 volts. Okay, and that is 53.2 minus 50, which is 3.2 volts. And that's about it. We can compute powers. We can compute voltages occurring throughout the circuit. And now I want to show you the effect of choosing a different reference node. So in the previous solution, we decided that this should be our reference node. So what I will do right now is I'll choose a different reference node, and we'll see how would that affect us. Frankly speaking, we can figure out that this will be our reference node. In that particular case, this is not 50 volts compared to the reference node. This is 50 volts compared to this node in here. So we can't just say that this is 50 minus 0. So we'll have to figure out what this voltage and so forth. So what I need to do is I need to write more or nodal equations in here. So I'll term these as maybe VA, and this will be VB, and this one here will be VC. But we should identify the A and the C in here are basically a supernode in here because we have the source in here. Okay, so what I will do is I'll treat them as such and I'll write a supernode equation. So technically we'll end up with a supernode equation in here. And then I call this here, this should be VB, for example. All right, so this will be a supernode equation. Or of course, I know the relationship between VA and VC, and I'll write another equation for VB. And from there, we'll go from there. We'll generate 3 equations and we'll find what the solution is, and hopefully we'll get the same VO. Just to point out, this voltage and this voltage and this voltage will be different than the previous solution. So in the previous voltage, VC was 0, and we computed what this voltage is. And now we're assuming that this will be our 0 in the circuit, and everything will be in relationship to this particular point. So let me write these equations. So I'll start with the VB KCL in here. So KCL at B. So KCL at B. And that will be VB minus VA divided by 80 plus VB minus VC divided by 50. So basically I wrote the one from here again. Even though the VA and VC are part of the supernode, you should keep them when you're writing these equations. And then here we have plus, I believe this is VB minus 0 divided by 40. So I have written 1, 2, and 3, and that's good. So we do that, and that's our first equation. Okay, that will be 0. We'll clean it up a little bit. And that will be this equation in here, minus 5A plus 23VB minus 8VC. And that will be our first equation. Okay, so we're going to have to write another equation. And the second equation will be the supernode equation in here. And just so that I know what we're doing, I believe we're going to be having 1 current, 2 current, 3 current, 4 current, and 5 current. So we have 5 currents in here. So let me just drag these down so that I don't have to scroll up and down. Okay, we'll drag in here. All right, so we do this here now at the supernode, Okay, so at the supernode, so let's start by these currents in here. Okay, so at the supernode, we will have VA minus, 0 divided by 800. We'll also have VA minus VB divided by 80 plus VA minus VB divided by 80. And then we ignore this current within the supernode. I believe we got these two here. That's good. So now we have the VC here. That's pretty much VC minus VB divided by 50. And then we have this current in here, which we already know. And that basically is 0.75 amp, because remember everything is in amps, not milliamps. And then we have the last one in here. It's actually here, because remember this is all part of this node. So this is leaving, we got that, we got this, and then we have that. And that's simply plus VC minus 0 divided by 200. And that should be 0. So let me count how many currents we have. 1, 2, 3, 4, 5. We counted 1, 2, 3, 4, and 5. So that's good. So we got the second equation. We'll clean it up. And after cleaning up, that will be the equation, and that will be the second equation here. Okay. All right. So the third equation we have, because remember we have VA, VB, and VC, so we need 3 equations. We wrote one for the VB, we wrote one for the supernode. Well, where do we get the third one? Obviously we can't write anything in here. This is the same as VC. Well, we know the relationship between VA and VC is simply VA minus VC equals 50. So the third equation in here is VA minus VC equals 60. Okay, so we can say just VA minus VC equals 50 volts, sorry, not 60. All right, so we do that, and we just basically do this here. We can just ignore that, and we can just say, well, this here is our third equation. So let's solve 3 equations with 3 unknowns, and we'll find the solution. So these are the 3 equations. It's VA, VB, VC in here. We have VA, VB, VC, and we have VA, well, VB is 0, VC, well, the scalar for VB is C, or the coefficient for VB is 0, and then VC. We just have to solve them. And here's the solution. The solution will be that VA is negative 3.2 volts, VB is negative 19.2 volts, and VC is negative 53. So this is the A, the B, and the C. So now what we're asked to do is figure out the output. And of course, you should pay attention that these voltages are completely different than before. So VA, before when the reference was here was 50 volt, now it's negative 3.2 volts. So what it tells me is, in reference to this point, this is negative 3.2 volts. It's lower. Okay, what matters is all the other voltages and the current on the circuit are the same. Just these node voltages and the way we use them are still the same. So I'm after V naught, so let's compute what that V naught is. Well, V naught is simply, well, it's negative VA because it is 0, because that's a positive in here, minus whatever the VA is in here, okay? And that simply is 3.2 volts. And hopefully it's the same answer that we got a few minutes ago, which it is. And you can double check your circuit. You can repeat the same analysis, but instead maybe use this as a reference point, or maybe this as a reference point. At the end of the day, just changing the reference, what it does, it just gives me different numbers for the other essential nodes. But if you're after like a current in here, all you have to do is just tell me, well, this is VB minus 0. Previously it was VB minus, or whatever that voltage in here minus this voltage in here, and so forth.